Okay. Uh, so actually we have found the complex exponential Fourier series representation for composite signal. That means with sinusoidal signals and cosinusoidal signal, sine and cos signal. Okay, so this kind of signal I gave you. Okay, this kind of signal I can't exactly remember. This kind of signal I gave you, and I asked you to find the Fourier series representation. Okay, then you no need to go through the um, principal example. Here you can directly use the Euler formula. Okay, so using the Euler formula also, you can represent this as a collection of complex exponential terms. So that is the Fourier series representation. No, so you can directly use the Euler formula. Okay. Uh, so before that, you need to find the overall period of this signal in naught. So I told you how to do it. You have to consider these two signals separately. Okay, then you need to find what is the uh, f or omega. This is a normalized frequency or normalized angular frequency. Okay, so here the normalized angular frequency is 5/2, 5/6. Okay, that means the frequency will be 2,5. So omega is equal to 2,5f. Okay, so f is equal to omega divided by 2,5. So that you can find the frequency f. Okay, then using f, 1 over f is the uh, period n naught. Okay, so in this way you can find the period. Okay, so here also you have to find the period. Okay, then you need to get the ratio of the first period and the second period. This period. Okay, this period if it is n01 and if this is n02, you have to get the ratio. Then you check this ratio. You need to check this ratio whether it is rational or irrational. Okay, so if it is rational, this is a periodic signal, and uh, uh, using that value, you can get the, for example, if n01, n02 is equal to x divided by y. Okay, so the overall period for this signal, for this composite signal, will be n0 01 y into n0 01 is equal to x into n0. Okay. So this is the overall period of the composite signal, the total composite signal. So you can find the overall period. Again, if you know the overall period, you can find the omega. Okay. So omega is equal to 2,5 by n naught. This is the fundamental angular frequency. Okay. So you can find it. Okay. Then you can find the corresponding coefficients. Okay. So that is the procedure. Okay. Very easy. Okay, so you should be familiar with this procedure. Okay, okay. So after that, I gave you another example related with Fourier transform. Actually, Monday class, I don't have time to give it. I didn't have time to give the example. Okay, so here under Fourier analysis, now we have done one example related with complex exponential Fourier series representation. Okay. Now we will do one example. So under Fourier analysis, we have two parts, Fourier series representation and Fourier transform. Under Fourier transform, we have discrete time Fourier transform, which is the DTFT. Then so this is the so here the omega is a continuous value, continuous variable. Okay. So if we need to get omega also as a discrete value, we need to sample this omega, the sample the signal in omega domain. So, so the sample version of DTFT we call DFT, discrete Fourier transform. Okay. So we have done one example from this one as I can remember. Okay. In previous week. Okay. And also I think we have done one example in the DFT also. Okay. Uh, So there are two uh, algorithm we use to calculate the DFT, that is time decimation FFT, fast Fourier transform, and frequency decimation FFT. Okay, so if we have time, we will do one example related with I think time decimation FFT is completed now by Dr. Udesh. So if we have time, we will do an example from here also. Okay, so before that, we will try to do one example with DTFT. Okay, so this example I have given in the class. Okay, so that is the example, that is actually example 2. Okay, so this is given in yesterday class. Okay, but for the Monday class, I didn't have time to give this question. So now I will give it. Okay, so I give you the question like this. Okay, now this kind of question I give you. First, find the uh, Fourier transform, discrete time Fourier transform of delta n. Okay, so this is very easy. This is the first question. Okay, and second, I gave you prove if the, okay, if xn Fourier transform of xn is x omega. Okay, and the vice versa also. Okay, okay, vice versa also there. If the Fourier transform of xn is x omega, okay, then prove e to the power j omega naught n xn Fourier transform is x omega naught. Okay, actually this is frequency shifting property. Okay, this is we called frequency shifting property. Okay, I ask you to prove this frequency shifting property. That is very simple. And third question I gave you. If xn Fourier transform of xn is x omega. Okay, now you get this xn, capital Xn. This Fourier transform will be 2 5 x omega. Okay, actually this is look like the duality property. This is look like the duality property. Maybe you have learned the duality property in signal and system. Okay, so continuous time signal, this duality property is valid for every time, but discrete time signal, sometimes this duality property is not valid. We are not defining a duality property for continuous time discrete time signal, but let's say that you are given for some condition this can be true. Okay, for some condition this can be true. Then I ask you to find. Okay, if this is there, I ask you to find the discrete time Fourier transform of xn is equal to 1. Okay, so these are the questions I gave you. Okay, so these are the 3 questions I gave you. Okay, so let's try to do this here. Okay, so we will try to do this quickly. Okay, this example. Okay, so this one is very easy. Can anyone tell me what is the answer here for discrete time Fourier transform of delta? Use the identity. Use the identity. So quickly tell me. What is the answer for this one? Okay, take 5 minutes and think. Okay, so we are going to find the discrete time Fourier transform of delta n. Okay, delta n. So you know the identity for a discrete time Fourier transform. That is if you have xn, and if you get the Fourier transform of this xn, okay, it will be x omega, okay, it will be x omega. I will put capital omega here, don't worry, okay, x omega, and it is equal to, sigma xn to the power j omega n, okay. So this is, uh, this can be from minus infinity to plus infinity, okay. So this is the Fourier transform, no? Is this correct? This one, okay. So this is the Fourier transform. That is correct. No, sorry, it is minus. This should be minus. Okay, this should be minus. So use this identity to find the DFT of this signal. Yes. Yes, the answer is correct. I got one answer that is correct. So what about others? So what is this delta n? What is this delta n? Delta n means the impulse. This is the unit impulse signal. This is the discrete time unit impulse signal. This is discrete time unit impulse signal. Unit impulse signal. Okay. The discrete time unit impulse signal is somewhat simple than the continuous time unit impulse signal. Okay. So you know that continuous time unit impulse signal, it is normally referred in delta t. Okay. So it is this kind of signal. Okay. We have put the arrow here and put one. Okay. This arrow means these signals go up to infinity. Okay. So what is this one? Um, I think, okay, we will see. Okay. We will see. I will do it. Okay. So that answer is not correct actually. I will. Okay. Okay. Uh, so, uh, so just listen. Okay. So if it is delta t, we put arrow here. Okay. We put arrow here. Yeah. Actually, this one is not the amplitude. Okay, this one is not the amplitude. Thank you for the answer. This is not the amplitude. Okay, for the discrete time signal, for a what is this called? Uh, unit impulse signal. Unit impulse signal. Here, this is not the amplitude. Actually, here, this one show the area. Show the area of this pulse, impulse. This is not a pulse. Okay, it is an impulse. Okay, so it is like this. If we have a pulse, okay, we know that we have a, definitely we should have a width, that is the time duration, width should be there. And there should be a height also, okay. That is the amplitude. This height is the amplitude and time duration and height. So this is a pulse, okay. So if you consider pulse, if you want to find the area of this pulse, that is nothing but h into width. That means amplitude into time duration. Okay. So this is the area of the pulse. Okay. Now impulse means the width should be zero. Width should be zero. So width is zero. So there is no time duration. So I told you that this is not practically generated because we can't generate a pulse with zero width. Okay, so practically this is not practical. This is not a practical signal. Okay, so this width will be zero. That means this time duration will be zero. Okay, in order to have the area one, okay, area one, this pulse, this height should be infinite. This height should be infinite. Okay, so actually for the impulse, this one is the area. If we need the amplitude, what is the amplitude here? Actually, what is the amplitude? This one is not the amplitude, one is the area. This A into T. In order to this one, okay, A into T should be 1. Okay. If this T is 0, what is this A value? The amplitude value should be what? No, no, amplitude should be not 1. You know that? If you get it, okay. So this is the pulse, okay. This is the pulse, okay. And you have amplitude and you have a time duration, okay. So if you want to find the area, now you have to multiply the amplitude with time duration, okay. Now if you consider a impulse, the time duration will be 0, A into 0, okay. But you need to have one area. You need to have one area. So area is 1, okay. The area is 1, okay. Area should be 1. Then what is the amplitude should be? The amplitude will be 1 divided by 0. What is that? Yes, infinite, okay. The amplitude should be infinite. It should be infinite, okay. So if you consider delta t, don't misunderstand this one as amplitude. It is the area, okay. Actually, the amplitude is infinity. Amplitude is infinity for delta t. So it is very complex mathematical signal, okay. It is not a simple signal. It is complex mathematical signal. Maybe you can remember the definition, okay. So if you have delta t, okay, and if you want to find the area, what you have to do, you have to integrate this from here to here. So you can get a very small duration, minus sigma to plus sigma, then you can integrate this minus sigma to plus sigma. So this is the area. So this will be 1. The area of the delta t function will be 1. Actually, that area is shown here, 1. Okay. So this is the definition. This is one definition. This is the definition for the unit impulse signal. Okay. Unit impulse signal. And also there are some properties. Maybe you can remember. Okay. So if you have any signal xt, and if you multiply it by st minus t naught, okay, and integrate it from minus infinity to plus infinity, you will get x t naught. Okay. So this is another property. Okay. Sometimes it is better to remember this property. For some application, we have to use this property. Okay. But not here for a signal and system stuff. Sometimes we have to use this. Okay. So this is the uh, continuous time unit impulse signal. Okay. Continuous time unit impulse signal. Now we are we are dealing with discrete time unit impulse signal delta. Okay. So here actually this is somewhat simple. Okay. This is somewhat simple, not much mathematical complex. Okay. So here n, your unit impulse, normally you have put a dot here like this. So this is the unit impulse and you put here 1. Okay. Actually this 1 is the amplitude. This is not the area. In case of discrete time signal, this is amplitude. Okay. But remember, in case of continuous time signal, this you have a arrow here and put 1. Okay. You have arrow here and put 1. Okay. So this is not the amplitude, that is the area. Okay. That is the area. So if you need much information, you can refer this book. Okay. Here also those informations are there and the signal and system. So these are the unit impulse signal, unit step signal. These are basic signals also. Okay, basic signals. Okay, so this is the basic signal, unit impulse signal. Okay, So yeah, you can see that there is an arrow, and here you normally put 1. Okay. So uh, yeah, so this is the so this is the definition. Okay, this is the definition. Okay, and okay, this is the equation I have given. Okay, this is one property. Okay, actually, you can you can you can use this property to get this one. Okay, so here there is no any time shifting. Okay, that means time shifting is 0. That means t naught is 0. So this will be 5 0. So same equation. Okay, same equations are there. So this is time shifted version. Here time is not shifting. That means the time shifting this t naught is 0. So you can put instead of this t naught 0. Okay, so that is okay. So these are the properties. Okay, and here you have the discrete time version also. Okay, unit impulse. So here you can here this is the definition. Okay, this is the definition. Un is 1 when n is greater than or equals c. Sorry, that is unit step signal. Here this one delta is 1 when n is equal to 1. If n is not equal to 1, it is 0. Okay. So this 1 is the amplitude actually. Here, this is the amplitude. Okay. So this is the definition for discrete time unit impulse sequence. Okay. So here, this value will be 1. You can directly get this value with as a 1. Okay. Now, I ask you to find the Fourier transform of discrete time Fourier transform of delta n. Now, I think you can do this. Okay. So you know what is the answer now. Okay. So if I use this one, this equation, if I use this equation, okay. So for a xn, the discrete time Fourier transform will be minus infinity to plus infinity xn e to the power minus j omega n. Okay, this is the discrete time Fourier transform. Discrete time Fourier transform of xn. Okay, xn मतलब Fourier transform. Xn Fourier transform of xn. This will be okay. So here now you need to find the Fourier transform of delta n. That means you need to find minus infinity plus infinity delta n e to the power minus 2 omega n. So what is the answer? What is the answer here? So very simple. Okay. So delta n is like this. This is 1. Okay. And e to the power j omega n will be like this. No? Like this. Okay. And here it is 1. Okay. Now if you multiply by this one, so you can see that these are 0 and these are 0. Okay. So for the multiplied signal, okay, this part will be 0 and this part will be 0. You have only this one. So 1 into 1, you will have what? Yes, that is 1. Okay, the answer is 1. Okay, so thank you. Okay, so this is the answer. Okay, so if you get the Fourier transform of delta n, the answer will be 1. What is the Fourier transform of delta t? What is the Fourier transform of delta t? Can anyone remember? What is the Fourier transform of delta t? Yes, that is also 1. That is also 1. How it happen? So for a continuous time signal, if you want to find the xt, Fourier transform of xt, that is, we have to integrate minus infinity plus infinity xt e to the power minus j omega t dt. This is the discrete, this is the uh, Fourier transform for continuous time signal, continuous time Fourier transform. Okay, this is discrete time Fourier transform. For a discrete time Fourier transform, instead of that integration, we have the summation only. But for the continuous time Fourier transform, we have the integration. Okay. So instead of this xt, we have to put delta t minus infinity plus infinity delta t e to the power minus j omega t dt. Okay. So you know that property. Okay. Minus infinity plus infinity xt delta t by t naught. This is equal to x t naught. Okay. So if this t naught, if there is no phase shift, that means t naught is equal to 0. So xt delta t, if you multiply it minus infinity plus infinity, it will be x 0. Okay. So the same property is there. Same type of signals is there. Instead of this xt, there is sorry. Instead of this xt, there is e to the power j omega t, and this delta t is there. Delta t is there. So once you get, if you multiply these two signal and evaluate this integration, you will have x zero. This x zero. That means you will have this one zero. This t will be zero. That means e to the power minus j omega zero. That will be one. Okay. So Fourier transform of delta t continuous time signal also will be 1. Okay. So this is not, maybe you can remember it, but no need for discrete time signal. Okay. This is the continuous time Fourier transform. Okay. So delta n, the Fourier transform of delta n is 1. If you have any problem, please ask. Okay. So I am doing this quickly because I hope already you have the idea. Okay. So delta n. So that is the 1 answer. Okay. Now I ask you to prove this one. So can you try to prove this? Can you try to prove this? It is very simple actually, not much difficult. Again, you have to use the definition for that. Okay. Okay. So let's say that you are given xn signal, xn signal. Okay. This is, if you get the Fourier transform of this xn, you will have x omega. You will have x omega. Now you multiply this x omega by e omega naught 10 term. Okay, then x. Now if you find the Fourier transform, you will have x omega minus omega naught. So you can see that this is the frequency, this is the frequency domain and it is shifting. Okay, so we call this frequency shifting property. Frequency shifting property. Okay, so there actually this is a standard property and standard derivation is there, the standard proof is there, okay, but using the definition for discrete time Fourier transform, okay, so you know the definition for discrete time Fourier transform, that is if we get the Fourier transform of xn, so we will have minus infinity plus infinity xn e to the power minus j omega n minus j omega n. Okay, so this is the definition. Okay, so now you can use this definition to find this sum, to prove this sum. So can you prove this? So just think for 5 minutes and try to do this, then I will do it. Okay. So use this sum. Okay. So you can you can so what you have to do is you can write the definition for this one. So it is already there. This is the definition. Okay, this is the Fourier transform of xn. Then you can write the definition. You can use this definition and write the Fourier transform for these terms also. Okay, then you can compare these two. By comparing, you can get this value. So very easy. So try. Okay, I will do. Okay, I will do. Just think how to do it. Okay. Okay. Now please write the Fourier transform for this term also. Fourier transform for this term also. Write the Fourier transform for this term. So what is the Fourier transform for this term? So if you get the Fourier transform of e to the power j omega naught n xn. Okay. So that is the Fourier transform of this term. So how we have? So it will be minus infinity plus infinity. Instead of xn, what is the term here? Tell me what is the term here? So Fourier transform of xn, you need to multiply xn by e to the power minus j omega naught n. Now you have e to the power j omega naught n xn. So what is the Fourier transform? So you have to multiply this whole terms, no? Okay, whole terms, that is e to the power j omega naught n xn should be multiplied by e to the power minus j omega n. So this is the definition for this one, this one. This is the definition for this one, expression for this one, okay? For this term, Fourier transform for this term, discrete time Fourier transform for this term, okay? This one, okay? Is this okay? It's okay, no? I haven't done any mistake, okay? Okay, now you can write this like this, okay? Minus infinity to plus infinity, xn. Okay, now this is e to the power j omega naught n, and here minus e to the power minus j omega naught n. So I will take minus jn. Those are common to these two terms. Okay, jn, then මේක දර්ශක දෙයක්. Okay, so if you multiply the same food, this power will be added. No, okay. එකම ආදේ දර්ශක වැඩි කරනකොට එකතු වෙනවා. Okay. So you will have, here I get the minus here. So this will be plus omega and this will be minus omega. Okay. So I get this one. I get this one. Okay. So this is the Fourier transform of e to the power j omega naught n xn. So now compare this one and this one. Compare this one and this one. Compare this one and this one. So now you can understand that, okay, you should understand this omega, okay, this omega is a variable, okay, this omega is a variable, it is not a constant, okay. So here, this omega is a variable, okay, and in this case, this omega is a variable and this one is a constant, okay. So omega minus omega naught also will be a variable. No, this one is variable, okay, although this one may be constant or variable. But if this one is variable, this terms also will be a variable, some variable, okay? Any variable, we don't know, okay? It can be any variable. Okay, like k or something, it can be any variable, okay? Okay. So now, if the variable is omega, okay, if the variable is omega, the Fourier transform of xn, Fourier transform of xn will be x omega. Okay. Now so this omega is the variable. Now here the variable is omega minus omega naught. That is also variable. This one same. Okay, same. Okay. So this omega into omega naught is identical to this omega. Both are variable. Okay. So if you get the Fourier transform of this one, if you get the Fourier transform of this one, okay. So that is not only a variable of omega. So that is a variable of omega minus omega naught. No? Okay. Yes. Okay. That is correct. Okay. So it is omega minus omega naught. Okay. So the Fourier transform of this one, Fourier transform, if you get Fourier transform of this one is a function of omega minus omega naught. Okay, so this omega naught can be variable or constant. Okay, so e to the power j omega naught n xn, the Fourier transform will be x omega minus omega naught if the Fourier transform of xn is x omega. Okay, so this is V proof. Okay, this is V proof. Okay, actually, this is the frequency shifting property. Okay, this is the frequency shifting property. And there is a time shifting property also. Okay, time shifting property. Okay, if we have time, we will try to do that one also. We will try to learn that one also, time shifting property. Okay. Uh, okay, now my questions. Now, so this one. Okay. Now this one. Okay. This one is there. Okay. Third question. Okay. Now tell me what is the, so take 5 minutes, maybe, yeah, 5 minutes. Take 5 minutes and try to solve this question by yourself. This question by yourself. Okay. So we have learned different things here. Okay, we have used different things here. Maybe the learned things you can use here also. Okay. So that is that kind of a problem. Okay. So it may be, it is just like an engineering problem. Okay. So you have learned something, then you have to apply them to solve a problem. Okay. So let's say that you learn these things. Okay. So you need to apply these things to solve this problem. Okay. Solve this problem. Okay. So try to solve this. Try to find the value for xn. Okay. Take 5 minutes. I think that's enough. Okay. So I got some answer. I think this this uh, this this is a data I have given you. Okay. This is the data I have given you. This data you wrongly understand. Okay. You misunderstand this data. That is the problem. Okay. Actually, this is the duality property. This is the this is the duality property for continuous time signal. In discrete time signal, sometime duality property is not defined. Okay, so I show you it. Okay, so for a continuous time signal, Fourier transform, properties of continuous time Fourier transform. Okay, so this is duality or symmetric. Okay, so this is the duality property. Okay, so what is this mean? Okay, okay. So if you have any signal, okay. So here this one is capital XT and this one is simple. Okay. So let's say that you have a signal XT. If you get the Fourier transform of this signal, you will have X omega. Okay. For example, let's say that, for example, okay, you have a t square plus 1, this kind of signal. Okay. If you get the Fourier transform of this signal, you will have, let's say that this kind of one, 2 omega plus 1 or something, plus 2 or something. This is not correct. Okay. This is not correct. I just give you example. Okay. So now this is the time domain signal and this is the frequency domain signal. Okay. This property said that if you have this one, if you have this one as a time domain signal, okay. So if you get the time domain signal of this one, that is 2t plus 2, and if you get the Fourier transform of this one, it will be 2 5. Instead of this t, you have to put minus omega here, actually not omega minus omega. So it will be minus omega minus omega square plus 1. Okay. So this is his status. Okay. So this is if xt is x omega, so this is another function. If you get that another function Fourier transform, so you can directly get it by substitute minus omega instead of this t. Okay, so that is this. Okay, so try to understand this one. If you have any problem, uh, please meet me and ask me. Okay, so I can explain this. So that is the duality property. Okay, so try to understand this. Okay, but for the discrete time signal, I think the duality property is not defined. Okay, as I can remember, duality property is not defined. So here the properties of Fourier transform, duality property is defined. No? Mm, it's a continuous time duality property. Here you can see that there is no discrete time counterpart for this property. Okay. So discrete time, so duality property, we are not using duality property for discrete time signal directly. Okay. So there is another duality between discrete time Fourier transform and discrete time, continuous time Fourier series. Okay. So that is another thing. Okay. So this is the duality. So this is, I don't know what is this. Okay. So this may be the for a continuous time Fourier series signal. Okay. Then you can find the duality between this one, discrete time Fourier and continuous time Fourier series. Okay. So that is another duality. Okay. So, so that basic duality property, this duality property is not applicable for discrete time signal. Okay. So that is why I told you this is look like duality property. This is look like duality property, not the duality property. But sometimes this may be correct. Okay. For some signal, this may be correct. Okay. So that is why I given you it as a data. Okay. So this is not always valid for any signal. Okay. This is not always valid for any signal. Okay. This is not always valid. Always valid. Okay. But to for only for this one, I just ask you to assume this. Okay. I just ask you to assume this. Okay. So so now, so you can see that. Okay. So if you have xn, if you have xn, the Fourier transform will be x omega. If you have xn, Fourier transform will be x omega. Now you need to find xn 1 using this property. Okay, this 1 using this property. Okay. Okay. You need to find this using this property. Okay. So I ask you to you can use this also. Okay. So you can see that if you get the Fourier transform of delta n, if you get the Fourier transform of delta n, that is 1. Okay. So if we get the inverse Fourier transform of 1, that is delta n. No problem. Okay. Now, if you want to find the DTFT, so of this one, okay, now you want to find the DTFT of this one. So it is directly equal to, so if you have any signal and if you have the Fourier transform, it's omega, then if you want to find the Fourier transform of this, okay, it will be 2 5 x omega, this 2 5 x omega, this will be, okay. So in the same manner, so you can apply this, okay. for delta n, Fourier transform is 1. Then for 1, Fourier transform will be 2, 5, this one. 2, 5, this one. That means 2, 5, 1. Not 1, 2, 5, delta n. Okay. So n, so we have to consider this n is the time domain. Instead of this n, we have to put omega. Instead of this n, we have to put omega. So it is not delta n, it will be delta omega. So the Fourier transform is 1 is nothing but 2, 5 delta omega. Correct? Okay. So this is it. Okay. Actually, this is correct. Okay. This is correct. Fourier transform is 1 is 2, 5 delta omega. I will prove it if you need. Okay. I will prove it if you need. Okay. So for this one, you can use this data, but this is not always valid. Okay. Don't get confused. Okay. I give you this data only for this question. එහෙම වෙන්න පුළුවන් නේ සමහර වෙලාවට සමහර සිස්ටම් වලට apply වෙන දේවල් තියෙනවා. හැබැයි ඒක commonly apply වෙන්නේ නැහැ. හරි? So that kind of things are there. Okay? So here, this is the answer. The Fourier transform of this one, okay? Fourier transform of xn1 is nothing but 2, 5 delta. Okay. Now if I ask you to find quickly, okay? Now if I ask you to find the discrete time Fourier transform of e to the power j omega naught n. Okay, e to the power j omega naught n. So if I ask you to find the DFT of this, what is the value? You can use this frequency shifting property. Use this frequency shifting property and try to evaluate this. What is the DTFT of e to the power j omega naught n? Tell me. Again you mistake, okay? Again you got a mistake, okay? Now you have to use this one and frequency shifting property. This one and frequency shifting property, and tell me the answer for this one. So I will tell you, I will give you the question. Okay. I will give you the question. The Fourier transform, discrete time Fourier transform of 1 is delta. Yes, that is the correct answer. Good. Okay, very good. Okay, so what about others? I got one correct answer. Okay, so you have to use this one. The Fourier transform of delta n, sorry, Fourier transform of 1 is 2, 5 delta omega. Okay, the Fourier transform of 1 is 2, 5 delta omega. Okay, then the frequency shifting property is j omega naught n xn will be x omega naught. This is the frequency shifting property. Okay, and with this is we know data. Okay, and you are asked to find DTFT of e to the power j omega naught n. So what is the answer? If you have xn, the Fourier transform will be x omega. Okay, and if you have ej omega naught n xn, Fourier transform will be x omega minus omega naught, frequency shifting property. Okay, so you know that for 1, the Fourier transform is 2, 5 delta omega. Okay, now e to the power j omega naught n into 1 will be, this is the xn. So it will be 2 5 delta. So I will put it here omega. So it will be omega minus omega naught. Okay, because this omega naught. Okay. So e to the power j omega naught Fourier transform is nothing but 2 5 delta omega minus omega naught. This is the answer. Okay. So this is what I told you to find. Okay. So we can see that. So you can use that property. Okay. And for example, try to find the Fourier transform of this one using the basic principle. Basic principle. So tell me what is the problem here. Okay. So you can't evaluate this actually. You can't evaluate that summation because it is infinity. There is the summation for infinity, minus infinity plus infinity. So you can't evaluate this summation if we are using the principal approach. Okay. So you have to evaluate, you have to use this properties and this data to evaluate the Fourier transform of this e to the power j omega naught n. Okay. So sometimes for some function, we can't directly evaluate the discrete Fourier transform, or it will be very hard. So that we have to use some properties. Okay. Okay. So that is what I want to tell you is that. So this is the answer. Okay. Okay. I hope you get it. So if you have any problem, please come and ask me. Okay. Okay. Now I will give you another question. Okay, now I will give you another question. So try to do it by yourself. Okay. Uh, so uh, I will give you it using the properties. Okay, using the properties. Mm, okay. Okay. So so this is the frequency shifting property. We have proved this and we have used this to solve the problem. Okay, you have used this solve the problem. Now this is the time shifting property. This is a time shifting property. Try to prove this. This is for continuous time signal. Okay. Let's do for the, okay. So this one also you can try. Okay. Try to prove, but not compulsory. Not compulsory. This is not compulsory, but the same approach is there. Okay. But for a discrete time, this is this is the time shifting property for discrete time signal. Discrete time signal. Now try to prove this. Try to prove this. Okay. So as a homework, try to prove this. Okay. So if so maybe next week we will try to do one question with regards to this one. Okay. Now try to prove this. Okay. As a homework. Okay. So we will stop. Okay. So we couldn't do anyway. Don't worry because uh, for your mid exam, you will get one question from sampling, one question for Fourier series, one question for discrete time Fourier series, one question for discrete time Fourier transform. So there will be three questions. One, two, three questions. Okay. Sampling, discrete time Fourier series, and discrete time Fourier transform. So you should be able to find the discrete time Fourier transform, complex exponential Fourier series. Okay. Discrete time Fourier series, complex exponential Fourier series. If I give you that kind of composite signal or repeated sequence. So repeated sequence means this kind of repeated sequence if I give you. Okay. If I give you this kind of repeated sequence, you should be able to evaluate the complex exponential Fourier series. Okay. So sometime maybe you have to learn how to plot magnitude plot and phase plot. Okay. We have done it in previous week. Okay. So it can be a composite signal or it can be a this kind of sequence. Okay. So for a both thing, you should be able to find this. Okay. for a discrete time Fourier transform also, you will get some questions. So maybe you are given a sequence and asked to find the DTFT. Or yeah, for the periodic signal. Okay, so I will give you a periodic the repeated sequence, that is periodic signal. Repeated sequence means periodic signal. Okay, repeatance means periodic. Okay, so Fourier transform for repeated signal or periodic signal, and you will ask some sequence and ask to find the DTFT. Maybe you will be given that kind of property, and you are asked to use that property. Then you have to learn. You have to use your practice to solve that. Okay. So three question will be there from sampling, Fourier series representation, and Fourier transform. Okay. So be ready for the mid exam. It is in 30th Saturday from 8 to 10. Okay. So try to do it. Okay. So if you have any problem, you can send me a WhatsApp message or email or call me. Then I will try to help you. Okay. Maybe I can help you. So if you have any clarification, I can help you. Okay. Uh, no. 8 a.m. to 10 a.m. 8 to 10. Only 2 hours. Okay. Right. Okay. So if you have any problem, you can ask me. I will be here for some time. Okay. And if you doesn't have problem, you can leave. No problem. Okay. Thank you for the participation. Sorry. Wait for a moment. I will. So you need to give the attendance. Okay. Please wait for a moment. Please wait for a moment. Don't leave. I forgot to get the attendance. No.